In this video, we're going to explore memory partitioning. We will specifically cover fixed and variable partitioning techniques. These techniques are very important in operating systems for managing how processes use the system's memory. Let's start with an overview of memory partitioning. Memory partitioning is a technique used by operating systems to divide the available physical memory into distinct regions. The goal is to efficiently allocate memory to different processes. This division helps in managing multiple processes in memory at the same time, while ensuring that they remain isolated from each other. There are several types of memory partitioning. We have fixed, also known as static partitioning. Next is variable or dynamic partitioning. Following is the buddy system. And lastly, paging and segmentation. Now let's delve into fixed memory partitioning. In this technique, memory is divided into fixed-size partitions. These partitions can be of equal size or of unequal size. Importantly, each partition can contain only one process at a time. The degree of multiprogramming, which is the number of processes that can run concurrently, is limited by the number of these partitions. Fixed partitioning is simple to implement and understand, but it has a drawback called internal fragmentation. As you can see in the example diagram, the operating system takes up 100 kilobytes. Then there are 4 partitions, each with a predefined size. These sizes can be different, as you can see, with partitions of 200, 150, 300, and 250 kilobytes respectively. Keep in mind that each of these partitions can hold only one process. Next, we will discuss the allocation methods used in fixed partitioning. We will start with first-fit allocation. In first-fit, the system allocates the first available partition that is large enough to accommodate the process. This involves scanning the memory partitions from the beginning and allocating the first partition that fits the process. The allocation time is fast, as it doesn't need to search the entire memory. However, this method tends to fill up the lower memory addresses first. It is simple to implement and provides fast allocation decisions. On the other hand, best-fit allocation allocates the smallest partition that is large enough to accommodate the process. This means scanning all partitions and choosing the smallest one that can fit the process. This method minimizes internal fragmentation, as it uses the smallest possible space. However, it requires a complete search of the memory table, making it slower than first fit. While it minimizes wasted space, it can create tiny, unusable fragments. Now let's discuss the limitations of fixed partitioning. One major issue is internal fragmentation, which is the wasted memory within a partition that is not fully used by the process. The inflexible partition sizes cannot adapt to the varying memory needs of different processes. Also, the degree of multiprogramming is limited by the number of partitions. Larger processes might not fit into any of the available partitions, leading to inefficient memory utilization. Fixed partitioning cannot take advantage of dynamic memory requirements. In the example diagram, we can see that the operating system takes up 100 kilobytes. Then there are 4 processes, A, B, C, and D, each allocated to a partition. However, each of these processes leaves some memory wasted within its partition, which is internal fragmentation. For example, process A, which requires 120 kilobytes, is allocated to a 200 kilobyte partition, resulting in 80 kilobytes of wasted space. Now we will explore variable memory partitioning. In variable partitioning, partitions are created dynamically, and each process gets exactly the amount of memory it needs. This approach avoids internal fragmentation. It leads to more efficient memory utilization. However, the partition size and location vary over time, which can result in external fragmentation. Variable partitioning requires a more complex memory management system compared to fixed partitioning. In the example diagram, you can see that the operating system takes up 100 kilobytes, followed by processes A, B, and C, each with different memory requirements. There is also a free space block, indicating available memory. Variable partitioning allocates memory dynamically, creating partitions of different sizes based on the process's actual needs. Now, let's discuss the allocation methods used in variable partitioning. First, we have the first fit method, which allocates the first free block that is large enough to accommodate the process. This involves scanning the memory from the beginning and allocating the first available block that fits. The remaining space in the block, if any, becomes a new free block, which we call a hole. The first fit method is fast and simple to implement. Secondly, we have best fit, which allocates the smallest free block that is large enough to accommodate the process. This method searches the entire list of free blocks and allocates the smallest hole that is big enough. While this minimizes wasted space, it is slower than first fit. In the example diagrams, you can see how each method selects different memory segments based on the process size. Let's explore the concept of external fragmentation and how memory compaction addresses it. External fragmentation occurs when the total free memory is sufficient, but it is divided into small, non-contiguous blocks. As a result, the system cannot allocate memory to a process, even when there is enough total free memory available. External fragmentation is a significant issue in variable partitioning and tends to worsen over time as processes are allocated and deallocated. One way to mitigate this issue is through memory compaction, which relocates all processes to one end of the memory, consolidating all the free space into a single large block. While this reduces external fragmentation, it is an expensive operation that requires significant central processing unit time. Additionally, it requires code to be relocatable, so that the processes can be moved without disrupting their execution. The diagram shows the before and after states of memory compaction, illustrating how fragmented free space is combined into one contiguous block. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.